Hi, in this problem, we're going to practice working with Poisson processes. And what we have is a sequence of light bulbs that we're going to start using starting at time equals 0. And we use them one after another. And as soon as one light bulb dies out, we immediately replace it with another one. And we have two types of light bulbs to choose from, type A bulbs and type B bulbs. And every time we have to choose a new light bulb, we pick type A or type B with equal probability. And also, whether we pick A or B for any one particular light bulb is independent of whether we pick A or B for any other light bulb. And the problem also tells us how long each light bulb lasts. And it's random. And for type A, we know that from the distribution that type A bulbs last for an exponentially distributed amount of time with parameter lambda equals 1. And type B bulbs last for an exponentially distributed amount of time with parameter lambda equals 3. And so type A bulbs last on average longer than type B bulbs. And the last thing that we're told is that how long any given type A bulb lasts is independent of how long any other type A bulb lasts, and also independent of how long any other type B bulb lasts. And the same thing for type B bulbs. Now, the first thing that we're going to look at is what is the expected time until the first failure? So we start out at time 0 with a new bulb, and we want to know how long is it going to take on average before that first light bulb dies. So let's call that T1. The time until the first failure. And what we want to find is the expected value of T1. Well, the first thing that we're going to notice is that this depends on whether the first bulb that we chose was a type A bulb or a type B bulb. So let's use total expectation, and we'll break that up into the two cases. So let's let A denote the event that the first bulb was type A. So we have the expected time till the first failure given that it was a type A bulb. We multiply that by the probability that it was actually a type A bulb. And then do the same thing if conditioning on the fact that it was actually a type B bulb. Okay, so what are all these values? Well, if we know that it's a type A bulb, then the time until the first failure is just the expected time until the first failure is just the expected value of an exponential with parameter lambda equals to 1, which we know for an exponential, the expected value is 1 over lambda. And so this conditional expectation is 1. The probability that we choose type A for the first bulb is, we know from the problem that it's just equal probability, so it's 1/2. Similarly, if it's a type B bulb, we know that the time is just the expected value of an exponential with parameter lambda equals 3, which is 1 over 3. And this probability is also 1/2 of choosing type B bulb. And when we add this together, we get that this is equal to 2/3. For part B, we want to find what is the probability that there's no failure before some arbitrary time t. So let's say this is some arbitrary time t here. What's the probability that there's no failure before this time? Well, if there's no failure before this time, that's equivalent to saying that the first bulb that we used, it lasted longer than t. So in terms of the random variable t1 that we defined, this is just what we want to find is the probability that t1 is greater than little t. And again, that depends on whether it's a type A bulb that we're using or a type B bulb. So let's use total probability here and break it up into the two possible cases. If it's a type A bulb, this is the probability. And if it's a type B bulb, we get this. And now we need to figure out what these different pieces are. If it's a type A bulb, the probability that T1 is greater than T is just the probability that an exponential random variable with parameter 1 is greater than some T. And from the exponential random variable, the CDF, or 1 minus the CDF, we know that that is equal to, in general, it's e to the minus lambda t. And so in this case, lambda is 1, and so this is just e to the minus t. And we get it 1/2 from the probability that it's actually type A bulb. And similarly, if it's type B, then it's the probability that an exponential random variable with parameter 3 is greater than t. And so in that case, it's e to the minus 3t times 1/2. And so that gives us our answer. Let's move on to part C. Part C wants us to know, suppose that we know that there was no failure in the first t time, or equivalently that the first bulb lasted more than t. What's the probability that this bulb was type A? So what's the probability that it's type A given that T1 is greater than T? And so in effect, we're now trying to flip this and calculate, try to infer whether or not it's type A based on the data that we collected, which is how long the bulb actually lasted. And so this is now going to be an application of Bayes' rule, which tells us that this is equal to the probability of that it's type A bulb times the probability that it lasted more than T, given that it was a type A bulb, over the probability that, the unconditional probability that it lasted more than T. Okay, so probability that it's A is 1/2. Probability that it's T1 is greater than T, given that it's A, we already calculated over here, it's e to the minus T. And the probability that, the unconditional probability, we just calculated in part B. So we'll substitute that in the denominator. And the answer that we get is this: 1/2 e to the minus T over 1/2 e to the minus T plus 1/2 e to the minus 3T. Okay. Now, part D asks us to find the variance of how long the first bulb lasts. So what is the variance of T1? To find the variance of T1, let's use this expression. The variance of T1 is equal to the variance of T1 squared minus the expectation of T1 quantity squared. We already know what expectation T1 is. It's 2/3. We calculated that in part A. But we still need to figure out what the expectation of T1 squared is. Now, expectation of T1 squared, we can again use the same sort of idea and break it up into the two cases. The first case that is a type A bulb, the second that is type B bulb. So this is equal to expectation of T1 squared, given that it's A, times the probability that it's A, plus expectation of T1 squared given that it's B, times the probability that it's B. Okay, and we know that given that it's a type A bulb, this T1 is now exponential with parameter 1. And so we know that from exponentials that the expectation of the square of an exponential random variable is just expectation of the square of a exponential random variable is 2 over lambda squared. And so in this case, for type A bulbs, lambda is 1, so it's 2 over lambda squared is just 2. So this is 2 times 1/2 for the first case. For type B bulbs, lambda is 3, so this expectation is 2 over 3 squared, or 2/9 times 1/2. And so we get 1 plus 1/9 is 10/9. And so after we substitute all that in, we see that this variance of T1 is equal to 10/9 minus 2/3 from part A squared, which is 4/9. That gives us 6/9 or 2/3. Okay. For part E, what we're told is that we have 12 failures, and we want to know what is the probability that the 12th failure is the 4th failure of a type A bulb. So let's draw out a timeline here, starting time 0. So here are some failures. So suppose that there are exactly 12 total failures here of either type. And we want this to be the 4th type A failure. Now, if that is the 4th type A failure, what does that mean for the previous 11 failures before that? That means out of the previous 11, there were 3 A failures out of 11 total failures. So the probability that we need to find is just exactly equal to the probability that we have 3 A failures out of the first 11, and the 12th failure was also type A. Okay. Now, what is the probability that out of 11, 3 of them were of type A? Well, that is just a binomial, because every single time we choose a new bulb, it's either type A or type B, and we said at the beginning that each of these choices are independent. And so if you think of choosing type A as a success, this is just the probability of 3 successes out of 11 trials. And then we also need the 12th trial to be a success as well. So combining that, we get that we have a binomial for the first 11. So we need 3 out of the first 11 to be successes, and the probability of success is just 1/2. And then we also need the 12th trial to be a success as well. And we can simplify this. This is just 11 choose 3 times 1/2 to the 12th power. All right. Part F. Part F asks a question that looks very similar to what Part E asked, except the difference is that now we want to know what is the probability that out of the first 12 failures, 4 of them were of type A bulbs. So 4A out of the first 12. So notice the difference here is that now the 4th type A failure is no longer fixed to be the 12th failure, the 12th total failure. This 4th type A failure could have happened earlier. So for example, it could have been that the first 4 bulbs were all type A, and the last 8 were all type B. That's possible now under Part F, but it was not possible under type E, or under Part E. So now this is actually a simpler problem to solve, because all we care about now is just 4 successes out of 12. So that probability is just 12 choose 4 times 1/2 to the 4th, 1/2 to the 8th. And so that simplifies as 12 choose 4 times 1/2 to the 12th. In Part H, we want to find the probability that 2 type B bulbs combined last longer than 1 type A bulb. Type B bulbs last for an exponentially distributed amount of time with parameter 3, and all times are independent from 1 type B bulb to another type B bulb. And so when you have 2 of them put together, it's just adding 2 IID exponential random variables. And so let's define random variable y to be the time of 2B bulbs. And because it's adding 2 IID exponentials, we have an Erlang random variable. And it has order 2 because we're adding 2 exponentials. And the parameter is the same as the parameter of the underlying exponential, which is 3. And given that, we can write what the PDF of this Erlang is. So fyy is 9y e to the minus 3y for y greater than 0. And we can do the same thing for one type A bulb. Let's call that t. T is the time that one type A bulb stays lit. And that is just exponential with parameter 1. And so we know what that distribution is as well. It's e to the minus t for t greater than or equal to 0. And so what we're asked to do now is really just find the probability that one of these is greater than the other. And we want the probability that 2 B bulbs last longer than 1 A bulb. So we can write that as the probability that t is less than y. And to find what that probability is, we can condition. So let's condition on y being some little y. So there's that conditional probability. Then we multiply that by the density of y at that little y and integrate. And we should integrate from 0 to infinity because that's the range of values for y. Okay, so what does that equal? Well, the first thing we can do is we can replace this random variable, capital Y, with some number, little y, because we're conditioning on y being equal to little y. And the second thing we can do to simplify this is we can actually remove this conditioning. And the reason for that is t and y are independent because t is related to the duration of A bulbs, type A bulbs, and y is related to the duration of type B bulbs. And we're told in the problem that these durations are independent. And so we can get rid of this conditioning. And now we just have this. So to proceed, let's fill in what these probabilities are. What is the probability that random variable t is less than y? Well, that is just a CDF of t. And t is an exponential. And so we know that the CDF of an exponential is just 1 minus e to the minus lambda t. In this case, it's going to be 1 minus e to the minus y because lambda is 1. And then we can also substitute in what the PDF of y is from earlier. It's 9y e to the minus 3y dy. And so the rest of this is just calculus. And if we finish the calculation, we'll get that the probability is 7 over 16. So that's one way of doing this problem. And so far, we actually haven't really seen a Poisson process appear yet. So let's try to come up with another method of solving this problem using Poisson processes. And there's a natural link because we're talking about light bulbs that die out according to exponential random variables. And then it has a natural connection to Poisson processes. So let's imagine this is time 0. And here is how long the first light bulb lasts. And we can consider this an arrival. So an arrival, we can think of it as just a bulb dying and being replaced by a new one. And these inter-arrival times are exponential. And so we do end, moreover, they're independent from one inter-arrival time to another. And so we do have a Poisson distribution. And so let's say this is when the next one dies out, and so on. So how can we solve this problem now with a Poisson process? Let's imagine that we're having a race. Starting at time 0, we have a race between type A bulbs and 2 type B bulbs. So they start off at the same time, and we want to see which arrival comes later. So we want a scenario like this. For example, if we consider a scenario like this, this means that a single type A bulb lasted for this long, which was longer than two type B bulbs combined. And so how can we come up with a probability now? What we can do is we can merge these two processes. And we can merge them because they're both Poisson processes and they're independent, because the arrivals, or how long the intervals for type A bulbs, which is how long type A bulbs last, is independent of how long type B bulbs last. And so these processes are independent. We can merge them. And so let's say we have some arrivals in the merge process. Now, in the type A process, what is the arrival rate? The arrival rate is type A bulbs lambda, which is 1. And for B, it's type B bulbs lambda, which is 3. And so in the combined, we get a lambda of 4. And so now, how do we actually come up with an answer for this probability? Let's consider the complement of this event. So let's consider t being greater than y, which means that the single A bulb lasts longer than both B bulbs. Now, how does that occur here in the merge process? What that corresponds to is exactly the case where we have the first two arrivals in the merge process, both are of type B bulbs. So if that is the case, that means that first a type B bulb died, and then the second B bulb died, and the type A bulb still hasn't died yet, which means that it has outlasted both of these. Now, what is the probability of this happening? Well, we know what the probability of an arrival in the merge process being from the type B process. That is equal to, in general, it's lambda B over lambda A plus lambda B. So in this case, it's 3 over 4. Now, so what's the probability of having a B followed by a B? Well, these are independent, and so the probability is just 3/4 squared, which is 9 over 16. That gives you the probability that the type A bulb lasts longer than the type B bulb. And notice that it could be the case that the very next arrival was type A, in which case the one type A bulb lasted longer than both of them. Or it could also be the case that there were more type B bulb arrivals until the first type A bulb. But it doesn't matter. As long as the first two were both type B, that guarantees that the single type A bulb lasted longer. So that, what we just found, is the probability 9 over 16 is the probability that t is greater than y. So to find the probability that y is greater than t, we just subtract that from 1. And when we subtract that from 1, we get that it is also the same answer, 7 over 16. So that's just another way of calculating the same probability. In part I, we're told that the process stops after exactly 12 total bulb failures have occurred. And we're asked to find how much of that time was illuminated by type B bulbs. So let's define some random variables. Let's call V the quantity that we actually want to find, the total time from type B bulbs. So in order to find that, we also need to know, out of those 12 bulbs that were used, how many were actually of type B? Because each time we choose either A or B randomly. So the number of B bulbs out of the 12 total bulbs is also a quantity of interest. And finally, let's let yi be the time of the ith B bulb. So how long did the ith B bulb out of these 12 last? All right, so given that, what we know is that V, the total time from B bulbs out of these 12, is going to be a sum of these individual times from each individual from each individual B bulb. And it's the sum of yi from I equals 1 to n. But notice that n itself is a random variable. So what we have is a sum of a random number of random variables. And what the problem asks us to find is the expected value and variance of v. So what is the expected value? The expected value, we can apply essentially iterated expectation, and we know that for a sum of a random number of random variables, where each one of the individual random variables is IID, and that's true because for all B bulbs, the amount of time that they last they're all exponentially distributed with parameter 3. So they are all IID. So in this case, we get that this expectation is equal to the expectation of n times the expectation of yi. And so what it's essentially saying is that on average, how many B bulbs do you have? And then multiply that by, on average, how long each B bulb lasts. And that will give you the total average time. And so what is that? What is the average number of B bulbs that you get? Well, you choose 12. Out of 12, you want to know how many of those were type B bulbs. But type A and type B bulbs are chosen equally likely. So on average, 6 out of these 12 will be type B bulbs. And each one is exponential with parameter 3. And so the expectation of an exponential is 1 over lambda. And so this is 1 over 3. And so the answer is 2 in this case. Now for the variance, we can go through the steps and use the law of total variance. But for the special case of the sum of a random number of random variables, we have a simpler formula, which is it's equal to the expectation of n times the variance of yi plus expectation of yi quantity squared times the variance of n. And so you see that there's two components of this variance. One component of the variance comes from randomness within how long each bulb lasts, and the other one comes from randomness with respect to how many B bulbs there actually are. And when you combine both of them suitably, then you get the total variance. And so in this case, expectation of n is again 6. Variance of yi is the variance of an exponential with parameter lambda equals 3. And that is equal to 1 over lambda squared. And so this is 1 over 9. The expectation of exponential yi is 1 over 3. Square that, you get 1 over 9. And the variance of n is the variance of the number of B bulbs out of 12. And so that n is actually a binomial random variable because it's the number of successes out of 12, where success is being a B bulb being chosen. And the probability of success for each trial is 1/2. And so for binomial, the variance is n times p times 1 minus p. In this case, it's 12 times 1/2 times 1/2, which is 3. And so what we get in the end, it's 6/9 plus 3/9, and that equals 1. In part J, we're given that there are no failures until time t, some time little t. And conditioned on that, we now want to find the conditional expectation of the duration of the first bulb, given that information. So let's draw a picture. Here is time 0, here is some t. And what we're told is that there are no failures from here until here. So no failures. Now, what we want to know is how long the first bulb lasts given that information. So what we can see here is that it seems like we can apply the memory list property of the exponential to help us. So for review, suppose that random variable x is exponentially distributed with some parameter lambda. And suppose we know that x is at least some little t. And given that, we want to know what the expectation of x is. So what we know is that we know that it's lasted until t. So it's at least that big. And from the memory list property, we know that going forward, starting from t, the additional time after t will also be exponentially distributed with the same parameter lambda. So it's as if it's starting over anew. And so this conditional expectation is actually going to be the expectation of x plus t. So you know that it's lasted at least, you know it's lasted t already, and then it's going to last an additional expectation of x. And so that's going to be 1 over lambda plus t. And so let's try to apply that. But we have to be a little bit more careful here because in our case, knowledge of how long the first bulb has lasted also gives us some more information about which type of bulb it was, because type A bulbs last longer on average than type B bulbs. So if T is large, then that gives us more confidence that this bulb is actually of type A, which will affect how long it will last subsequently after time t. And so it'll be, this problem J will be a combination of using this, the memoryless property, plus some inference about whether it was type A or type B. So in part A, we already calculated what the expectation of some random variable T1 is, where T1 is defined to be the duration of the first bulb. All right, so in part 1, we calculated the expectation of T1, unconditioned on anything else. But now we want to calculate the conditional expectation, the expectation T1, given that T1 is greater than T. So if you remember in part A, the way we did this was we used total expectation and split it up into two cases. One where the first bulb is of type A, and another where the first bulb is of type B. And we can do the same thing here. So we can split this up into the conditional expectation T1 given T1 is greater than T, and the first bulb is type A. And then we have to multiply that by the probability that it's actually a type A. But another difference here is that, remember, we're in the conditional world that T1 is greater than T. So this probability also has to be conditioned on T1 being greater than T. And we have a similar expression for the case where it's a bulb of type B. All right. So now let's figure out what this conditional expectation is. The conditional expectation T1, given that it's at least T and it's of type A. So now that we know that it's of type A, that has fixed what distribution T1 has. T1 now we know is exponentially distributed with parameter 1. So now we can go back to this memoryless property and use what we found there. So this is in fact equal now to the T that we know has lasted already, plus an additional expectation of a exponential with parameter 1. So it's T plus 1. Or we can also get that from here, 1 over lambda plus T. Now, what is the probability that it's actually a type A, given that it has lasted until time t? Well, that we've also already calculated. We calculated that in part C. And from part C, the answer that we got was 1/2 e to the minus t over 1/2 e to the minus t plus 1/2 e to the minus 3t. Okay, and now let's do the second one. What is the expectation of T1 given that it's at least T and that it's a type B bulb? Well, now, given that it's type B, T1 has been fixed to be an exponential with parameter 3. And so this conditional expectation is T plus 1 over 3. And the probability that it's B, given it's T1 is greater than T, is just 1 minus this probability, because it has to be either A or B. So 1 minus this expression here is just 1/2 e to the minus 3t over 1/2 e to the minus t plus 1/2 e to the minus 3t. And we are essentially done, because this is the answer. We can simplify it a little bit and write it as t plus 1/3 plus 2/3 times 1/2 e to the minus t over 1/2 e to the minus t plus 1/2 e to the minus 3t. So if we can group this like that, what we know is that given that it's lasted until t, we know that the total time is at least t. Plus, there's going to be more on average, depending on what type of bulb it is. So if it's a type B bulb, then we know on average it'll last an extra 1/3. And if it's a type A bulb, we know it's going to last an extra 1. So regardless, on average, it's going to last an extra 1/3. And then if it's a type A bulb, it'll last an extra 2/3 on top of that, on average. And so that gives us the final answer. So in this problem, we've covered a lot of different parts and problems related to Poisson processes. And we started out with looking at the perspective of exponential random variables, and then we tried to relate that to a Poisson process. And in the end, we also combined some elements of inference as well. So I hope that was helpful, and see you next time.